All right, hi everyone. So today I'm going to finally be making the videos for Unit 4 that I've been promising that I would do. Happy Friday the 13th. Spooky season continues, right? All right, so like I said, we're going to be doing Unit number 4 today. So I'm going to be taking a look at PowerPoint number 1, and that's talking about the fundamental trig identities. So really, this entire unit is about trigonometric identities. So just in this PowerPoint, we're going to be taking a look at some of the fundamental ones that we need to know. All right, so again, if you check the Schoology page, right, this is going to be under Unit 4, under Material, and this is PowerPoint number 1. All right, so let me share my screen and let us begin. So today we're going to be talking about the fundamental trig identities. Okay. So our objective for today is students will be able to derive and identify the 5 fundamental types of trigonometric identities. Notice, all I said was derive and identify. All right, we're not going to be verifying. We're not actually going to be doing any math. We're going to save that for the next PowerPoints. This first one is just an introduction to get us used to the idea of what derivatives are, or not what derivatives are. Cut that out. Get used to the idea of what identities are. All right, and how we would use them in trigonometry. All right. So what is an identity? An identity is a mathematical statement that is always true, no matter which values you plug into the variables. All right, so notice there's a few key things right here, right? We're talking about a mathematical statement, for one. We're also talking about variables. There's going to be variables in this mathematical statement, and we can plug in any numbers or any values for that number, right, into the variable, and it will always be true. Okay, that's the key part. It'll always be true. So it's like a fact, right? So here's an example, and I'm taking you back a little bit to Algebra 2, and hopefully you guys remember this example, right? A plus B squared, right, in parentheses, squared, is equal to A squared plus 2AB plus B squared. Right, so hopefully you remember this. No matter which numbers you plug in for the value of A or which number you plug in for B, this statement is always going to be true. All right, so we're going to be doing the exact same thing when it comes to trig and trig identities, except we're going to be using our 6 main trigonometric functions. All right, so it's going to be like this. It's just going to be a mathematical statement using trig functions where we can plug in any angle, right? Because we know when we're doing trig functions that we're using angles, right, into the variable, right? So we can plug in any angle into the variable. And what's our variable? Theta. All right, so that means we're going to be looking at a bunch of different mathematical facts, right, where we can plug in any number for theta and it's still going to be true. Okay, let's keep going. All right, so there's going to be 5 fundamental types of trig identities. Okay, and you don't have to write all of these down just yet because I'm going to go through them one at a time, but just so you guys know, right, we're going to have reciprocal identities, quotient identities, Pythagorean identities, cofunction identities, and even odd identities. Okay? I promise you already know half of these. I've been secretly instilling this knowledge in your brains the whole time. Okay? So it'll be all right. We're going to go through one at a time. But like I said, you already know a lot of these based on the math that we've already been doing in units 1, 2, and 3 prior to this. Okay? So let's start, right? Our first one that we're going to be taking a look at is our reciprocal identities. All right, so let's recall from the past when we were in unit 1 or 2, I believe, and we were calculating the reciprocals in our calculators, right? And what did I tell you? You can just do, for the reciprocal function, you can just do 1 over its reciprocal, right? So cosecant and sine, those are reciprocal functions, right? So to get cosecant, we can just do 1 over sine. Plug it into the calculator, and that's our answer, right? Secant goes with cosine. So secant equals 1 over cosine, right? And cotangent goes with tangent. So cotangent equals 1 divided by tangent, right? So hopefully this rings a bell because this is what we did when we were plugging it into our calculators, right? Now, just really quickly, I want to make it clear that the reverse is also true. Oh, I forgot to fix this in my PowerPoint. Give me 1 second. I fixed it. All right, let me go back to sharing my screen. I'm not going to edit this out. Okay, and present. All right, so like I was saying, right, we've got secant equals 1 over sine. no, sorry, cosecant equals 1 over sine. Secant equals 1 over cosine, cotangent equals 1 over tangent. Well, we'll also add in the reverse. The reverse is also going to be true, right? So sine equals 1 over cosecant, cosine equals 1 over secant, and tangent equals 1 over cotangent. Okay, so the reverse is also true. All right, that's it. You now know 6 trig identities, right? That is all of the reciprocal identities. These are all the fundamental basic ones you guys need to know. Everything else will be based upon this, right? So these right here that are outlined in this orange-red box, write these down, all right? These are 6 key important ones that we need to know, right? Let's keep going. Now we're going to be talking about number 2. So this is the quotient identity. It's also called the tangent identity. So to understand this identity, right, we actually talked about it before, but just to recap, right, we're going to be taking a look at the unit circle, and we're going to be defining tangent. Well, first we're going to be defining sine and cosine, right, but then also tangent in terms of x, y, and r in the unit circle. So here we're taking a look at the unit circle, right? So we've got in all of our angles, all of our coordinate points, our x, y axis, our circle, right? And remember how when we created this little triangle based off of the terminal side, right? The terminal side that's created by this angle in here, right? This gray angle, right? We made a little imaginary triangle in the middle of this circle, right? So here at the bottom, this leg of this right triangle, right? This bottom leg, this corresponds actually to the x value or the x coordinate point of this spot on the circle right here, right? So where the inside meets the outside, that's the radius, right? Where the inside point meets the outside line on the circumference of the circle, right? That line, that length, that is our radius, that's r, right? The x value of this point right here is actually this leg of the triangle right here, this bottom leg that lies along the x-axis, right? And our y value of this point right here is actually the length of this side of the triangle right here, right? Because that talks about the height that we're moving on the y-axis, right? So this coordinate point right here would be x comma y, right? Well, now if we're taking a look at this reference angle in here, right? Okay, here we go, x comma y. If we're taking a look at this reference angle right here, right? Let's do a little bit of math. Let's go back to SOHCAHTOA and let's remember cosine and sine, right? Oh, I jumped the gun on that one a little bit, right? Okay, sorry. Let's remember cosine and sine, right? So if cosine is adjacent over hypotenuse, then that means that for cosine, right, it would be x over r, right? We're looking at this angle down here. Adjacent is x, our hypotenuse is the radius r. Well, when our radius is equal to 1 in the unit circle, then cosine is equal to x over 1. And x over 1 is just x, right? So that means the cosine of this angle is equal to the x value of this triangle, right? The x coordinate point, yeah, that's actually going to be the x coordinate point. So no matter how big, right, we open up this triangle, no matter where this radius is in the triangle, the x coordinate point is actually always equal to the cosine, right? Same thing goes with sine, right? Sine is opposite over hypotenuse, right? So sine is going to be y over r, and if r is equal to 1, then sine is y over 1, and that's just y. So no matter what type of little triangle we would make in here, right, our y coordinate point is actually the value of our sine for that angle, right? Let's remember that. So that's how we come up with this coordinate point, x comma y, being equal to cosine of the angle, comma, the sine of the angle, right? And now taking a look at tangent, right? So if we're looking at this angle in here, right, tangent is opposite over adjacent. So y over x, right? So tangent is opposite over adjacent. So here it would be opposite y over adjacent x, right? So now, if we were to substitute y and x for cosine and sine, right, we would find that tangent is equal to sine, y, divided by cosine, x. All right, so tangent of the angle the tangent function of the angle in this circle is equal to the sine function divided by the cosine function of that angle, okay? And cotangent, right, because we know that it's the flipped version of tangent, instead of opposite over adjacent, it would be adjacent over opposite. It would now be cosine over sine. So cotangent of theta, cotangent function of that angle, is equal to the cosine function value divided by the sine function value for that angle, all right? Those are our other two identities, right? These are the two quotient identities, AKA the two tangent identities. So there we go. We talked about this in class before, and I've been saying it again, but I really wanted to break it down one more time just so that it's clear, right? We already knew these, yeah? So these are our next two functions. Like I said, you guys already know half of the identities. So you knew the reciprocal ones. You should have already known the quotient ones. But if you didn't, now you know, right? So let's keep going. We've got Pythagorean identities, all right? So let's just recall, let's go back in our brains and recall the Pythagorean theorem, right? A squared plus b squared equals c squared, yeah? The Pythagorean theorem is another identity, basically, right? You can plug in a squared and b squared, and then you will always get an answer for c squared, right? You can't plug any numbers into c squared, but you'll always get an answer, right? Okay. So that's why it's called a theorem. They don't really call it anything, whatever. Okay. I'm getting into technicalities. That's not the point. The point being, right, that when we apply this to the unit circle, right, we're no longer be going to looking at A, B, and C. We're going to be looking at X, Y, and R, all right? Notice, I don't have R written here. Why? Well, because the radius in the unit circle, right, this black line right here, the radius is always equal to 1 in a unit circle, right? X and Y, they'll change, right? These coordinate points, right, X and Y, they change, they become different. But the radius of the circle is always the same. And we know that for any circle, right? If you take the radius of the circle, no matter whether you take it from here to here, or here to here, or here to here, the radius is always the same, right? The radius in the unit circle is always equal to 1. All right, so that means when we're applying the Pythagorean theorem to the unit circle, x squared, right, the leg, one of the legs, x squared, plus y squared, the other leg, right, is always going to be equal to 1 squared, and 1 squared is just 1. So that's how we derived this second little formula right here, right, x squared plus y squared equals 1. Well, we have to take this back a step, right, or not back a step, but we have to take this one step further, I mean. Notice how before, right, I told you that the coordinate points, x and y, correspond to cosine and sine, right? We just talked about that. X and y are the same thing as cosine theta and sine theta. So we can actually replace x squared with cosine squared, and we can replace y squared with sine squared. So cosine squared theta plus sine squared theta is equal to 1. So that is how we come up with our first Pythagorean identity. So intuitively, you guys already knew this one too, right? Because you already knew the Pythagorean theorem. So all we had to do was just take it a few steps further and actually apply it to plugging in trig function values and applying it to the unit circle as well. So that's our first Pythagorean identity, all right? Make sure you write this one down. Cosine squared theta plus sine squared theta equals 1. Let's keep going. There's a few, oh, and here's another actual visual for that, right? So no matter where you draw this little triangle, right, your x value, right, on the x-axis, that's always equal to your cosine, and your y value on your y-axis, right, that's always equal to your sine. So x comma y is the same thing as cosine comma sine. The radius is always 1, and this angle can be whichever angle in the triangle. That's why we just call it theta, right, because this is just a variable. Right? So there's two other Pythagorean identities, all right? Again, bear with me, this requires a little bit of algebra just to prove. I don't care that you guys know how to prove them, I just wanted to show you guys where they come from. All right, so let's start off with the one we just learned, cosine squared theta plus sine squared theta equals 1. And now we're just gonna do a little bit of math, a little bit of fooling around with this so that we can find our next Pythagorean identity. All right, so what we're going to do is we're going to turn these into fractions. and create common denominators. All right, well, not really. We're just turning them all into fractions. We're dividing the entire identity by cosine squared theta. Why you would do that in real life and for whatever purpose, I couldn't tell you, but just to prove the next identity, this is the way that you would do it, right? So we take cosine squared theta, we divide that by cosine squared theta, plus, right, we take sine squared theta, divide that by cosine squared theta, and then that equals 1 divided by cosine squared theta, right? This should still be true. All we did was just mess with the function a little bit, but this is still a true statement, right? Now, notice, cosine squared theta divided by cosine squared theta, that cancels out, that equals 1. Sine squared theta divided by cosine squared theta, well, we know from the quotient identity, right, that sine, or that tangent is equal to sine over cosine, right? So sine squared divided by cosine squared is equal to tangent squared, right? And we know also from the reciprocal identities that we just used, right, that we just learned, that 1 over cosine is equal to secant, yeah? So 1 over cosine squared is equal to secant squared. So that is how we get our second Pythagorean identity, right? This reduces down to 1. Sine squared over cosine squared is equal to tangent squared. And when we add those together, those are equal to 1 over cosine squared, which is the same thing as secant squared. So here, we just reduce the fraction to 1. Here, we use the tangent identity, right, the quotient identity, to come up with tangent squared theta. And here, we use the reciprocal identity to come up with secant squared theta. All right, so we already knew actually how to do all of these rules when we created our second Pythagorean identity right here, right? So this is our first Pythagorean identity, this is our second Pythagorean identity, and now we're going to do our last Pythagorean identity, and instead of dividing by cosine squared, we're going to divide by sine squared, all right? So now when we divide by sine squared theta, right, we get cosine over sine, which we know is cotangent, right? It's not tangent, it's cotangent, right? And if it's cosine squared over sine squared, then that's going to actually reduce down to cotangent squared, right? And then sine squared over sine squared, that's just equal to 1, right? Just like x over x is equal to 1. 2 over 2 is equal to 1, right? Sine squared theta over sine squared theta is equal to 1. And then just like how we did before, right? 1 over cosine was secant. Well, 1 over sine is cosecant. So then 1 over sine squared is cosecant squared. So that is how we get our last trig identity. All right? Cosine squared theta over sine squared theta is cotangent squared theta. Sine squared theta over sine squared theta, that just reduces to 1. And then 1 over sine squared is cosecant squared. Again, this right here, we derive this from the tangent or the quotient identity. This just reduces to 1. And this one, we got this from the reciprocal identities. So same thing, right? So let's make sure we have written down all 3 of the Pythagorean identities now. Okay, let's keep going. So now we're going to go on to cofunction identities. All right, so I'm going to take this back to the basics. I'm going to take us back to the first week when we just had this basic 3, 4, 5 right triangle, right? And we were just talking about SOHCAHTOA, right? So now if we take a look at cosine of A, right, we're looking at angle A down here. Cosine of A is going to be equal to 4, right, the adjacent side, over 5, right? So SOHCAHTOA, so for ka, right, C-A-H, that's cosine is adjacent over hypotenuse. So the adjacent side is 4, the hypotenuse is 5. So cosine of angle A is equal to 4 over 5. Right? So far, so good. Again, this is review from the first week of school. All right, now let's take a look at sine of angle B. So we're looking up here now at angle B. Well, sine is SOHCAHTOA, right? S-O-H, so, right? So we should have sine equals opposite over hypotenuse. So if we're looking at this angle up here, the opposite side is actually 4, right? That's the side that opposes the angle, the side that's opposite of the angle. So it's 4 and the hypotenuse is 5. So the sine of B is 4 over 5. Oh, well, what do you notice here? The cosine of A is the same number as sine of B. Curiouser, right? Also keep in mind, okay? So we're gonna keep that back to mind. The cosine of A is equal to sine of B. Keep that in mind. And then also keep in mind that A and B are complementary, right? So A plus B equals 90 degrees. Well, if we remember, right, we should remember at this point that 90 degrees is the same thing as 2 pi radians, right? So that means that A plus B is equal to 2, or not 2 pi, I'm sorry guys, pi over 2. Yeah, it's written here correctly, all right? That 90 degrees is the same thing as pi over 2 radians, or half a pi radians, right? So angle A plus angle B are equal to pi over 2 radians. So that means that angle A is equal to pi over 2 minus B, and angle B would be equal to pi over 2 minus A, right? So this is how we get our co-function identities, all right? So sine, right, of pi over 2 minus theta equals cosine theta, all right? So the sine of A is equal to the cosine of B, and cosine of A is equal to the sine of B. Cosine of A is equal to the sine of its complementary angle, and sine of A is equal to the cosine of its complementary angle, right? So this is just our little bit more advanced way of saying cosine A equals sine B, right? And instead of having to write A and B and having two different variables in these identities, we're just using one variable and we're representing the complementary angle by pi over 2 radians minus theta. So this pi over 2, you can call this B, right? Cosine of A is equal to sine of B. All right, and sine of A is equal to cosine of B. That's all that means, all right? So this is a fancier way of saying this fact. So this identity might feel a little bit new, but I'm hoping that it kind of makes, when you look at it this way in its more simple form, cosine A equals sine B, I think that that comes kind of intuitively, right? Because we can see it for ourselves. The 4 over 5 is 4 over 5, right? But this is the more mathematical way of writing out what's actually happening here. All right, so sine of pi over 2 minus theta equals cosine theta, and cosine of pi over 2 minus theta equals sine theta. Right? So let's write these down. These are our two starting cofunction identities. All right, so cosine of an angle is equal to the sine of its complementary angle. That's all that's happening here. Okay? Now, these rules actually apply to the other trig functions, right? So tangent goes with cotangent, secant goes with cosecant, right? These aren't very common ones to use. They're not very common in general, right? I guess none of trig is, but whatever, that's beyond the point. That's okay. So notice that tangent of the complementary angle is equal to cotangent of the angle. Cosecant of the complementary angle is equal to secant of that angle. All right, and that applies for the rest of the 4 trig functions. So just take a second, write these down, pause me if you have to, but I'm gonna keep going, right? So that is the cofunction identities. Now we're gonna take a look at the even and odd identities, all right? This one I think is going to feel the most foreign, right? Because usually when we think of even and odd, we think of like even numbers are divisible by 2, right? Like 2, 4, 6, 8, like that's what even means. And odd numbers are not, like 1, 3, 5, 7, 9. Right? That's usually what we think of when we think of conventional even and odd numbers. That is not what it necessarily means in trig, okay? So when we're talking about even and odd identities, I'm gonna have us recall our coterminal angles, right? And just the fact that we can have negative angles in a circle, yeah. So we're just going to take a look at the positive and negative angles, right? We know that here we've got cosine, comma sine, cosine, comma sine, right? Here we have positive theta, and here in the red we've got negative theta. Again, positive is counterclockwise, negative is going clockwise, all right? So notice that, oh, this might be in the way, all right? Cosine stays positive when the angle becomes negative. What does that mean? All right, if we're taking a look at these coordinate points right here that are created by our angle within the circle, right? If cosine is our x value, right? Cosine is positive right here when theta is positive. But now let's take a look when theta is negative, right? Take a look at negative theta. Well, cosine again is our x value. Oh, cosine is still positive. So despite the fact that our angle became negative, cosine stayed positive. Cosine stays positive. So we call this even, right? So because cosine doesn't become negative, cosine stays the same, we call it an even function. So that's what even means in trig, all right? And because cosine and secant are inherently tied, right, because they're reciprocals, the same applies for secant. So secant is even too. Secant is going to stay positive even when an angle becomes negative, all right? Sine is a little bit different though, right? So if we're looking at positive theta, right, sine, our y value, is positive. But when we take a look at negative theta, right, sine, again, our y value, is now negative. Sine has changed. Sine has went from positive to negative. So because it becomes negative, when the angle becomes negative, sine is considered an odd function, all right? And because sine and cosecant are related, cosecant is also an odd function. So when theta is negative, sine and secant become negative. But when theta becomes negative, cosine doesn't. Cosine stays positive, right? That's all you need to know. So this is how we come up with our next few identities, right? Cosine of the negative angle is still positive. Secant of the negative angle is still positive. It's a little hard to see here, but this is a plus sign in the front. It's not a negative sign, it's a plus sign. All right? And then when we're looking at sine of the negative angle, or negative theta, is negative, right? The negative angle, sine becomes negative, and the same thing goes with cosecant. So cosecant of negative theta is in fact negative cosecant, all right? And now we're going to take a look at tangent and cotangent. Tangent and cotangent are also odd functions, all right? So that means that tangent of negative theta is going to be negative, and that cotangent of negative theta is also negative, all right? You don't have to worry about the terminology so much. I don't care that you know that something is even or odd. That's not really the point. But the point is that you understand where these 1, 2, 3, 4, 5, 6 identities come from. Right, so that's where these 6 identities come from. Make sure you write these down. All right. And now here's a summary of all of the 5 types of fundamental trig identities. You guys learned all of these in one day. It's beautiful. It's incredible. We did it. All right. So that's everything. That's everything for PowerPoint number 1. So in our next few PowerPoints together, we're going to actually be doing some verifying. We'll do some actual math. We'll see how we can actually apply these to do different things. But I just wanted you guys to get a basic understanding for what these identities are and what some of the most fundamental and most commonly used and important identities are in trigonometry. All right. See you guys in the next video. Bye-bye.